This presentation is primary-secondary versus variable primary flow. It's conducted in 5 parts. The first 2 parts describe the operation of 2 popular chill water pumping configurations. The second 2 parts describe issues surrounding low delta T syndrome in variable chill water loops. And the final part details design and control considerations for increasingly popular variable primary flow systems. Let's start with the ideal operation of primary-secondary, including its advantages and disadvantages. Here is a typical primary-secondary system. Over on the left, we have a primary loop where the flow is going pretty much in this direction. In the secondary loop, the flow is going in this direction, and we have a common pipe in between, which takes care of the excess flow from here to that's not required by here. You'll notice that we have a dedicated pumping arrangement. Doesn't mean that primary-secondary doesn't come in headered pumping as well, or a combo of the two. It's just that most of the time I see dedicated type pumping. One of the more important things to take away from this particular part is that load is equal to flow times delta T. Load is equal to flow times delta T in the chiller, in the chiller's evaporator, in the condensers, in the coils, in the system, in the cooling tower. Everywhere flow is equal to, or load is equal to flow times delta T. Now, in a primary-secondary system, the primary load is equal to flow times delta T, but delta T varies with load. That's why it's in red. In the secondary, load varies with flow, but it's still load is equal to flow times delta T. An understanding of that equation makes it pretty easy to troubleshoot troublesome systems. Number 1 rule of primary-secondary is that the primary flow must always be equal to or greater than the secondary flow. If this is not done, then the system will go out of control. Literally, the bypass that you saw earlier, the decoupler, the common pipe, would have flow running through it backwards, so that 56-degree water would be mixing with the 40-degree water, increasing the temperature that's going to the coils. The coils would then open up all their valves, and it would spiral out of control. So, number 1 rule of primary-secondary, primary flow must always be equal to or greater than secondary flow for the system to work. This doesn't mean you can't use the bypass as a means of control. For example, allow bypass flow backwards to indicate that it's time to add more pumping into the primary loop. Here is numbers attached to that same diagram we saw before, where we have 56 degrees cooled down to 40 for a 16-degree delta T. At 100% system load or design, we have 6,000 tons worth of chillers, 3 2,000-ton chillers, 9,000 GPM, going from 56 to 40, as I said earlier. And we're going to make the assumption that we got around 100 feet of pressure drop. So that's what these secondary pumps are sized for, is 9,000 GPM at 100 feet of pressure drop. At the design point, the flow in the primary is equal to the flow in the secondary, so there is no flow through the common. At 75% load, we're going to make the assumption, which is not bad under ideal circumstances, that the flow and the load track one another, meaning that if the load is 75%, then the flow is 75%. 75% of 9,000 is 6,750. So we now have 6,750 flowing in our variable flow loop over here. In our constant flow loop, we still have 3 chillers running because we need them. We can only get to 67% load with shutting a chiller off, so all 3 chillers got to run. So all 3 pumps are running, and 9,000 GPM is being produced. And the excess, the difference between 6,750 and 9,000, goes through the bypass. That's this 2,250. At 50% load, we'll be at 50% flow. 4,500 is 50% of 9,000. Over in our secondary loop. And over in our primary loop, we can now shut off a pump, and we can shut off a chiller. We can shut off a pump because the remaining pumps is 6,000 GPM, so we have not violated rule number 1 of primary-secondary, which is that the primary flow must be equal to or greater than the secondary flow at all times. So the excess, the difference between 6,000 and 4,500, would go through our bypass, and everything is working very nicely. And when we get to 25% load, we now can shut 2 chillers off. Our secondary is going to be 25% of 9,000 GPM, or 2,250. We have 1 pump running, so that's 3,000 GPM in our primary. So the excess, the difference between 3,000 and 2250 is 750, goes through our bypass. That's how the system ideally is supposed to work. Advantages of primary secondary is that it's easy to control, it's easy to commission, it's very well understood by the consulting engineering community, it's very well understood by operators because it's been around for many, many decades. Disadvantages versus VPF, since we're comparing it to variable primary flow, which is VPF, is that there's a higher pump energy cost because I do have primary pumps that are all on constant speed drives and therefore using more energy than what a VPF system is with one set of pumps, all at variable speed drive. Another disadvantage is it has a higher installed cost than a VPF system. You've got secondary pumps because there's two sets of pumps here. Secondaries pumps, you have piping for those pumps, you have valving for those pumps, you have rigging and wiring and controls, strainers. All these things are going to increase the cost over a variable primary flow because I need two sets versus just one. And it's more susceptible to low delta T than what variable primary flow is because it can be more forgiving, though it suffers from low delta T as well. This is the end of chill water piping types, part 1.